In previous video, we mentioned that densities are among one of the quantities that can characterize rectifiable subsets of Euclidean spaces. In order to study that quantity, we have to start with subsets of Euclidean space Rn, and you can already begin to think that E has positive Lebesgue measure so that it's truly n-dimensional and not of a smaller Hausdorff dimension. And also recall the fact that the Lebesgue measure on Rn agrees with the Hausdorff n measure. And that was one of the videos in the Hausdorff measures playlist that I will put a link to in the description of this very video. So what is the density of a set at a point x? So notice that x does not have to belong to the set E. The question that the Lebesgue density theorem is concerned about is what can we say about the following ratio for very small scales. If you take a ball of radius r centered at x, how much of that ball lies within the set E? To rephrase, how much of the ball does the set E pick up? Of course, the Lebesgue measure of the ball is independent of the center and given by omega n r to power n, where omega n is a global constant which agrees with the volume of the unit ball in Rn. Therefore, in the theorem, in the denominator, you will see omega n r to n and not Lebesgue measure of the ball. But the first formulation is just saying, is easier to immediately see that what the fraction is showing us is the percentage of the ball that lies inside the set E. Lebesgue density theorem, which I have stated here, is this amazing fact that if you have any measurable subset of Rn, then almost every point in E has density 1. That means this limit exists and is equal to 1. If we translate that to the language of percentages, this is saying that almost 100% of the ball lies in the set E. And the second part says that if your point is not in the set, then almost none of the ball will be inside the set E. To illustrate how deep and how remarkable this theorem is, I will look at some examples beginning with stupid ones and then giving you a more interesting one at the end. And toward the end of this video, I will mention other applications of this theorem and how it's proved, but I won't give you the proof. So the simplest measurable sets, for example, one can look at are open sets. So if you have a very nice domain with C1 boundary, so E is interior of this, is open, and boundary of E is a C1 curve, then it's easy to see that if you are inside the set, then density must be 1. That limit up there, when it exists, we call the density at x of the set E. And if you're not in the set closure of E, then balls centered here when radius goes to 0 are fully outside the set, so you get 0 there. And if you're right along the boundary, then a ball centered there, when you zoom in, the curvature contribution and complications will go away and you will be basically looking at just half of the ball. So in that case, this limit as r goes to 0 of that ratio will be equal to 1/2. So let's say that is our example 1. Example 2, so alter a set E by adding or removing a null set. Then a density, whether it exists or not first, and the exact value of it does not change anywhere. This is because in the numerator you are talking about the Lebesgue measure of something, and if you alter any set by a null set, the Lebesgue measure does not change. So that quantity doesn't change. So therefore, whether the limit exists doesn't change, and when it exists, the quantity of that limit also does not change. So could we break the theorem, the claim of the theorem, by playing around with null sets? The answer is no, because the theorem already has this almost everywhere in the statements. So it claims that things are going to be this way only up to a set of measure 0. So if you had the claim true for the original set, then it will, by default, will be true for the new set, because the only thing that has changed is that some points used to be in E and now are in E complement, and vice versa. But those again only contribute a set of measure 0. So for example, you can think about a dense countable set E inside Rn or R2. Then the density is 0 everywhere for every x in R2, whether it is in E or not. The claim of the theorem part 2 is good. For part 1, for some points in E, we could have expected that we would get density 1, but we have density 0. So those are the points that quotation violate the claim of the theorem, but only they constitute a set of measure 0. So that's our second one. The next example, I won't even show you the calculation. The square, the closed square in R2, there you get 4 different behaviors. So in the interior, you get densities. So the possible densities are 1 if you are in the interior, 0 if you are in the complement. If you're along the interior of the edges, you get 1/2, and if you're at the corners, you get 1/4. In all of these examples that I showed you in particular, one fact was true, and that was that the density actually existed, that limit existed. But it does not have to be that case. So my next example will be of a set where what we call the upper and lower densities do not agree. So again, the setting is that you have a measurable set in Rn, and you have a fixed point in Rn, either in E or not, doesn't matter. Then, okay, so we don't know when that limit exists. And fortunately, due to this beautiful invention of lim sups and lim infs, we can always take a limit anyway. So that's why I love these notions of lim sup and lim inf. So R goes to 0 always exists. So to show that we're taking lim sup, we put a star up in the superscript. So this will end density of E at the point X. Notice that this quantity is dependent on X, but also on the set E. And the lower density, I bet you can guess, will be the limit infimum as R goes to 0 of the same quantity. So density exists if and only if lim inf equals the lim sup. One remark that may seem trivial, but it will be meaningful when we study densities for arbitrary subsets of larger Euclidean spaces is that in this particular case, because the numerator can at most be just the bit measure of all of the ball, and therefore each of these fractions is never bigger than 1, even not necessarily when r goes to 0, for every positive r and every point x. So in particular, this will be less than 1 for every x in Rn, whether it is inside E or not. So you always have this upper bound for that, and the problem is whether the lim-inf agrees with lim-sup. And in the next example, in this example we're looking at, I'm going to say no. So I want to build a set where for some point, which will be my origin, the upper and lower densities do not agree. So here my set will be all of R2 minus a countable union of some balls that are going to be disjoint and shrinking as k goes to infinity and converging toward 0. So the first ball, B1, that is removed is sitting here, and the distance of this point from here to the origin is R1. So this is like the farthest point from the origin, and this is like the larger circle. So this is the disk at the origin x of radius R1. And then there is this, actually this is like dot dot dot, so that means it's not up to scale. So that's what they do in map making, that, well, you should imagine this is much longer than the picture probably shows you. Okay, so to do this construction, imagine none of this was there. So you took a huge ball of radius R1, and from that you removed B1. And what did you follow in removing this B1 was that B1, its volume, is at least 10% of the volume of the large ball of radius R1. So definitely you can just resize your B1 to be like that, and B1 and that big ball are touching along one point. It's not really that delicate to have this particular geometry, but I try to draw the simplest pictures that I can. And then you move closer. So in this case, next ball B2 will be much closer to origin, and R2, which is where you are going to place your next ball and your next removed ball, is much smaller than R1. You can imagine that what you see in here inside this green box will be maybe 1 million times zoomed. So if necessary, I don't think we need that extreme of restrictions, but if we need to, we can. So the reason I'm not giving you particular values is because, well, first of all, it's insignificant and it will make it more technical, and things will look more complicated than they really are. So all we care about, the properties that we care about, is that the tails in the sequence of balls become really small, so that if you look at the volume of, I really want to keep that picture on my screen. So you want to look at the volume of all these blue balls after a threshold. So if you want to look at all of them starting at next value and going up to infinity, is just about or less than or equal to the Lebesgue measure of ball Bn. So that means if you're looking at this ball and then you look at every ball that will be following here, all of this summation, if they kill themselves and try really hard, they will be just as much as B2. And the reason I'm saying, like, if needed, you can imagine you're moving 1 million more, is because if you wanted even much less contribution from the whole tail, you could just afford to do that. So this will give us a control of how much volume is removed from the inside of the big, huge balls. For example, this will show us the following. If you take the Lebesgue measure of ball X centered at R n, and you intersect with the E, and then this will be, by the way, this doesn't have to be in R2, just imagine it's in Rn. So, and then this is 0, because I will forget to write R2, I will keep n, so let's just keep it in n dimension, and you can imagine these balls are spheres and in higher dimension. Anyway, so how much is at most removed? So this will be the volume. Okay, so from this huge one, there is 10% remove in the very first ball. So here is my Rn, and I'm looking at this huge ball here. So 10% is removed right here with the ball Bn, and the remaining removed balls, as we said, contribute at most as much. So that will make it 20%. So the most you can remove is 20%. So the remaining part will be at least 80% of the ball of radius x and r n. Okay. From this calculation, we can actually give a lower bound on the upper density. Okay, so this is equality. Okay, this is equality. So the lower density of E at the origin will be smaller than, of course, if you take any one particular sequence of radii, in this case rk, as they go to 0. So this will be ln of b 0, my x is 0, rk intersected with e over omega n rn rk to power n will be 0.8. So it will be percent precisely. So the reason I cannot claim more is that maybe there is some other way of picking your radii which gives you even worse. So at least this is immediate from that fact. But then I want to give a lower bound on upper density. And for that, I choose a new sequence of radii. So this time what I will do, notice that the worst that happens to my collection, to my balls, the biggest removals happen right at R1s. If I pass that and then I take a radius here, so if I look at this radius here and remember this dot dot dot, that means whatever you see inside here is 1 million times smaller, then in effect I haven't removed anything from this ball, and the ratio of the volume is almost 1%. Almost nothing is removed from that thing. And that is where this part comes in, that the next radius is much, much smaller than the first one. So there's this huge part, huge gap here. Again, the hugeness is hidden inside this dot, dot, dot for me to be able to draw the picture, because I cannot draw at a scale of 1 and then 1 over 10 to the power 6 at the same time. So there is this huge part where nothing has been removed from. And we can require, in fact, that the next radius is so small that even if I just be generous and give away every volume that is inside here, again, I don't lose much. And therefore, I can make the upper density. So I choose this, for example, as capital R1, and then the next R, capital R, will be here, R2. So I will jump over these removals, the blue removals, and then take the radius right after that. So in this way, I will avoid having a big portion, a big percentage of my balls removed. By choosing this capital RK as in pictures, again, this is already complicated to explain. Imagine I had some more algebra with that, which was unnecessary. So we can guarantee that the upper density, which is the highest possible ratios that you can maintain as you approach 0, will be, say, at least 90%. But again, you can get as close to 1 as you wish. On the other hand, you can make this as small as you want. Anyway, the conclusion is that there is this 0.9 which is a lower bound for the upper densities of E at X, and then it's strictly bigger than 8%, which is an upper bound for the lower densities of E at this origin. So at origin, density does not exist. So it took us a little bit to get through this example, but I think it was worth it. So the Lebesgue density theorem then says that this cannot happen for many points, like the origin in this case. And that in itself is kind of surprising. So the next, I think this will be my final example, will be that if we construct Cantor sets by removing at a fixed ratio at every stage, then it will have 0 measure And this is something I had also mentioned before. So in any way you construct a Cantor set, by whether self-similar or not, if you assume that at every stage you remove, say, 1% of the volume, and for the next stage you remove 1% of the previous ones. If you construct any Cantor set this way, then it cannot have positive measure. Why? Because having positive measure, so proof using the Lebesgue density theorem, if this Cantor set had positive measure, then there would exist, according to the Lebesgue density theorem, almost every point inside C is a density 1 point, but so there would exist some x in C such that density is 1. But by construction, when you take a ball, at least that percentage of it is removed. The density is less than 1 minus alpha for some alpha positive. So therefore you cannot have a density 1 point, and therefore you cannot have the Cantor set have positive measure. If Cantor set has measure 0, this is no problem because the Lebesgue theorem does not penalize null sets. It doesn't require null sets of showing any particular behavior. Again, then that's a nice example. For example, even in R1, that is good to know. So one way actually to see sometimes that sets have measure 0 is to show that they cannot have density points. So the Lebesgue density point is an amazing tool, both in geometry and in analysis. For example, it allows to define approximate continuity or approximate derivatives. So basically, for example, for derivative, you need a notion of an open ball. So if you want to say a function is differentiable at a point, okay, you want to take a limit as you approach the point, so you need an open ball around it to be able to do so. What if your set doesn't have open points? For example, you have a measurable set, A, and then you have a function defined on A only a priori. You want to talk about derivative, but then A may not have even one interior point. Imagine you start with some A, and then you remove a dense subset of Rn from Rn. Therefore, A has no interior points, but still F kind of deserves to have a notion of derivative at some point. That is where you can define derivative at density points. Density points are effectively measured theoretically the interior points of a measurable set. One example that I thought about when I first was met with this notion of density was having an exponential decay along here. So for x positive, suppose here, and your set is everything here, here. So the exterior of your set is this blue region here. Then 0 is a density point. So imagine you have a function, f of x is 1 in E, which is here, and then 0 in Rn minus E. Then f is approximately continuous at 0. Even approximately differentiable, the derivative being 0, because f is basically the constant function of 1 from the viewpoint of measure theory. So in the neighborhood of x, effectively everything is just what happens in E. And that has proven to be an effective tool in analysis. So I promised that I will mention how this theorem is proved. So Lebesgue density theorem is an immediate corollary of Lebesgue differentiation theorem. So this is a different kind of differentiation that you may be used to. We're not talking about derivatives as in calculus, as slopes or anything, but rather about differentiation of measures with respect to one another. So it's a very kind of more abstract generalization of derivative, but so here you talk about derivative of one measure with respect to another, and whether you can recover one measure by integrating some density with respect to the other measure on the set A. And the proof of that uses the more complicated Besickovich's theorem. More complicated, when I said I meant more complicated than the 5R Vitalik covering theorem. So for this theorem, you cannot afford to dilate the balls to do a covering. You have to cover with the original balls, because for an arbitrary measure, you don't know how the measure of 5 times the ball compares to the measure of the ball itself. With the Lebesgue measure, we know it at most multiplies, not at most, it exactly multiplies by 5 to n. But with arbitrary Radan measures, for example, that's not possible. Anyway, these are all very complicated stuff, and I don't plan to get into the business of Lebesgue differentiation theorem, at least for this playlist, maybe in future for measure theory and Sobolev functions. But the Lebesgue density theorem is a consequence of that one. Okay, and the final remark is that this density theorem holds for all finite Borel measures. So if in the ratios, in the fractions that we looked at, if you replace this ln by the Borel measure of the ball centered at x intersected with E, and then you compared it to the Borel measure of the ball xr, then the Lebesgue density theorem in the more general case for non-Lebesgue measure is saying that this limit is equal to 1 almost everywhere inside the set E. And here this almost everywhere will be like this new measure almost everywhere. And the proof is the same by using the Besickovich's covering figure. Okay, so now that we know this behavior of arbitrary measurable subsets of Rn, in the next video we'll be able to define density for n-dimensional, say, subsets of a larger Rn, so kind of embedded in there. And also we will define density for not necessarily integer exponents. And then in future videos, we will talk about general theorems that we can prove about these densities. Okay, we have a long way to go, but we want to enjoy the journey much more than the end results, which exist everywhere anyway. Okay, let me know which examples you liked, if you have any questions about the examples, if you thought about interesting sets where the claim of the Lebesgue density theorem is not actually easy to see right away. But with that, I say thank you for watching this video so far, and have a great one.